Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast covers thermodynamics. The first thing I'm going to talk about are the 4 laws of thermodynamics. Then I'm going to get into enthalpy, entropy, and Gibbs free energy. And I'll talk a little bit about what you need to know on the MCAT in terms of those and what types of questions you're going to see. And then lastly, I'll talk about the 3 different types of heat transfer. That is conduction, convection, and radiation. And this material will show up on 1 out of the 4 sections, which is the Chem Phys section of the MCAT. I hope this podcast gives you a little bit better of an understanding of thermodynamics, which is going to be on the MCAT, a little bit of a harder topic, I would say, in terms of chemistry. It's not always straightforward, a little bit non-intuitive. So I hope this podcast helps. All right, so the first thing I want to talk about here is the difference between kinetics and thermodynamics, because they're 2 opposing forces. So kinetics is essentially the speed of the reaction, whereas thermodynamics is more related to equilibrium of the reaction. So to kind of illustrate this, I want to talk about the reaction in which diamond is converted to graphite. So someone out there hopefully that's listening to this is engaged. I want you to look down at your engagement ring. And it looks like diamond, right? Well, hopefully it looks like diamond. It doesn't look like graphite or it doesn't look like carbon. So this reaction is a spontaneous reaction. In other words, diamond spontaneously converts to graphite. This reaction has a Gibbs free energy of -3 kilojoules per mole, which indicates a spontaneous reaction. However, when you look at the kinetics, you'll see this reaction is really slow. For instance, it would take about 10 billion years for this reaction to go to completion, where you go from diamond all the way to graphite. So just for illustration purposes, let me run the calculations real quick. So it would take approximately 10 billion years for a piece of diamond to convert all the way to graphite. So what I want you to keep in mind while I talk about thermodynamics is that this is only basically half of the material that describes a reaction. It essentially tells you which side of a reaction is favored, the products or the reactants, but it doesn't tell you shit about how fast a reaction is. For that, you'll have to know kinetics, which will be the topic of a different podcast. All right, so let's get into the laws of thermodynamics. So I'm first going to give you kind of the straight up definition of each of these laws, and then I'll try to kind of convert that more into English and tell you what it really means, and then how to apply it, and then talk about how you may see it on the MCAT. And thermo is somewhat non-intuitive, so I'm going to do my best to make this clear. However, if you are looking for, good videos that describe thermodynamics, go to YouTube. Khan Academy is great. You can look up other videos, and hopefully at the end of it all, you can kind of get a clearer picture of what some of these thermodynamic variables mean. All right, so there are 4 laws of thermodynamics: the 0th law, the 1st, the 2nd, and the 3rd. Let's start with the 0th. The 0th law of thermodynamics states that if 2 systems are in thermodynamic equilibrium with a 3rd system, then the 2 original systems are in thermal equilibrium with each other. In other words, if system X is in thermal equilibrium with system Y, and then system Y is in thermal equilibrium with system Z, then X and Z are also in thermal equilibrium with each other, which it brings me back to like those 5th grade math properties. I forget whatever it's called, but like the transitive property or whatever. Anyways, so, take 3 objects, let's say your hand, a metal pan, and a stovetop burner, right? So if you turn that stove burner onto high, you put your pan on there, and then you put your hand on there, eventually, and probably pretty quickly, all 3 will be the same temperature, right? At which point you can say they're in thermal equilibrium. So this is just saying that if your hand is in thermal equilibrium with the stovetop, then the pan must be also in equilibrium with both of them, which makes sense, right? This is a pretty easy law to understand. And I don't think I've seen this law come up too much on the MCAT, but I could see a scenario where maybe they give you three bodies that are in thermal equilibrium and, in a passage or something. And then they say, which law of thermodynamics does this scenario apply to? So I could see something like that, but this one is probably less important than the other laws. So let's get on to the first law of thermodynamics. The first law says that thermodynamic energy, which is heat, can neither be created nor destroyed, just transferred. So you'll see an equation that goes along with this that is, and delta U is equal to Q plus W, where delta U is the internal energy, Q is heat, and W is work. And what this equation is saying is that the change in internal energy of a system is equal to the heat input plus the work done on the system or work done by the system. So it's saying that a transfer in internal energy is either due to, number one, the input or output of heat directly, or by work that's either done on the system or by the system. So to increase the internal energy of a system, you have to input heat or input work. And so you can see here, you can't create this internal energy. You have to basically transfer it from somewhere else into this system. So that's kind of what the first law of thermodynamics says. It's a conservation of energy law. And you'll probably see this a few different ways on the MCAT. The first is asking questions related to that equation. Delta U is equal to Q plus W. And so W can be calculated, again, which is work, can be calculated as P delta V, or pressure times the change in volume. This is known as constant pressure work. So the first type of question I could see them asking is something in which you have to manipulate this equation, delta U equal to Q plus W, in order to solve for something. So, maybe they give you a passage where they're talking about the lungs and they're talking about a change in volume as you inhale, and then you're asked to calculate the heat, and it tells you in the passage the internal energy change is 0. So in this case, you'd set this equation to 0, and you'd have Q plus W is equal to 0, and then you put in P delta V for work, and then you just go through and you solve for the Q using the pressure they give you, the change in volume of your lungs, and then you solve for that Q. So these would be pretty easy calculations to do. It's just knowing that equation. You also might be asked to identify the actual definition. So, they might talk about conservation of energy or conservation of thermal energy in a passage, and then ask you, which law of thermodynamics is this, which the answer is the first law. All right, on to the second law of thermodynamics. This law states that the entropy of an isolated system always increases. And you may see this also as the entropy of the universe always increases, because the universe is kind of the ultimate isolated system. And your Gen Chem teacher might have told you a story about how, what happens after you clean your room? Well, eventually your room becomes messy again because entropy must increase. What I like to think about is you take two gases. So let's say I have gas A in my right hand, gas B in my left hand, and now I mix those gases. So what I just did is I increased the entropy, right? I increased the disorder because I mixed these two gases together. Now I dare you to take this mixture of gases and pull each gas apart back into each hand. It's impossible, right? This process of taking a mixture of gases and pulling each constituent gas out of it is a decrease in entropy. So you can see, obviously, the universe tends to favor these processes that increase the entropy. It just seems more natural, it's kind of a weird concept to really look at, but just know for isolated systems, entropy is always increasing. In terms of the MCAT, you might see this as definitional. So again, this is the second law of thermodynamics. Or you might see something where they throw in something like delta S universe is greater than 0, is less than 0, equal to 0, as part of an answer. Well, just know that the right answer has to be that the delta S universe is greater than 0, right? It's always increasing, so it's got to be greater than 0. And I actually had a friend, or I guess probably more of a peer in college, who actually got a tattoo, and I'm not even doing a bit. This is real. He had a tattoo that was delta S is greater than 0 on his calf. And I think it was supposed to be kind of like a deep metaphor for something, but anyways, I'll never forget that delta S is greater than 0 because I sat behind him, so I was forced to look at it every day. All right, on to the third and final law of thermodynamics, and that is that the entropy of a pure crystalline substance at 0 Kelvin is 0. And all this is doing is basically giving you a reference point so that you can determine absolute entropy instead of just change in entropy. This basically sets that 0 point. It's like being able to say, today it is 35 degrees Celsius, instead of just saying, oh, today it is 3 degrees warmer than it was yesterday, or we had a delta T of 3. Right? This gives you a reference point, like Celsius, which is a freezing point of water, is 0. So it gives you that reference point so then you can set absolute values. And there's an equation that goes along with this third law, which is that entropy at some phase change is equal to the enthalpy of that phase change over the temperature of that phase change. And phase changes occur at a single temperature. I'll talk more about this in a little bit, but just know that that equation goes along with it. S is equal to H over T. And so where will you see this on the MCAT? Well, you'll see it in terms of the definition. You'll want to know this is the third law of thermodynamics. And then you'll also probably see some kind of calculations regarding a phase change. Maybe they give you enthalpy, they give you temperature. You got to calculate the entropy, which is that S equal to H over T equation. So it's important to kind of keep in your back pocket for use, but really a simple calculation. So let me just quickly summarize these 4 different thermodynamic laws. The 0th law has to do with equilibrium between bodies. If X is in equilibrium with Y, which is in equilibrium with Z, then X and Z are in equilibrium with each other. The first law says that energy is always conserved. Specifically, thermodynamic energy is always conserved and cannot be created or destroyed. The second law of thermodynamics says that entropy is always increasing in an isolated system, or that delta S is greater than 0. And then the third and final law of thermodynamics says that the entropy of a pure crystalline substance at 0 degrees Kelvin is equal to 0. All right, so you're likely to see quite a few different thermodynamic variables on the MCAT. So that's what I'm going to talk about next. The first is going to be entropy, then enthalpy, Gibbs free energy, heat capacity, equilibrium constant K, and then the reaction quotient, which is Q. So I'm first going to cover the more kind of less known variables, and then I'll go over enthalpy, entropy, and Gibbs free energy in a lot of detail. So heat capacity is this variable, either Cp for constant pressure heat capacity or Cv for constant volume heat capacity. It's a term that describes how much energy it takes to raise the temperature of some substance by 1 degree Celsius. In other words, it's describing how good something is at absorbing heat. And so just for the record, water is the GOAT when it comes to heat capacity. It's got super high heat capacity, I think 4.1 something joules per Kelvin. So since water has this really high heat capacity, it's used a lot of the time for coolant. So, let's say a nuclear reactor, you have a coolant system that pumps around water. You're able to take heat away from that reaction by running cold water over, a reaction vessel or whatever. And that water will absorb a lot of that heat and then be moved away. So it takes some of that heat away. So just know water, super high heat capacity. Heat capacity is how much energy it takes for a certain substance to be raised by 1 degree Celsius. And water's is around 4.1 joules per degree Celsius. And that number is per kilogram of water. So that unit should really be joules per kilogram per degree Celsius. The next variable you should know is the equilibrium constant. And all this is the products over reactants, each of these terms raised to the power of their coefficient. So for instance, take the breakdown of ozone, which is O3, and that breaks down into O2 and oxygen, just O. And so you take the products, which are O2 and O, divide that by the reactant, which is O3, and each of these has a coefficient of 1, so it's just raised to the first power. And together that is the equilibrium expression, or K. It's also called the equilibrium constant because at equilibrium, this value is always the same. It's constant. It's K. The reaction quotient, which is Q, is the same exact thing as the equilibrium expression, only you are not at equilibrium. So this Q is not a constant. It can change because you're not at equilibrium. If you were, it would just be K. So what's important to know here is what the relative difference between Q and K mean in terms of the reaction that you're looking at. So there's three scenarios. The first is that Q is equal to K. The second is that Q is greater than K. And the third is that Q is less than K. So when Q is equal to K, your reaction is at equilibrium. Duh, right? Q equal to K, it's just K. When Q is greater than K, then you have too much product, and therefore your reverse reaction is favored, right? Because Q and K are both equal to products over reactants. So if Q is greater than K, you have way too much product. On the other hand, if your K is greater than Q, then you know that you're in a state in which you have too little product and too much reactant. So in this case, the forward reaction is favored, and you go through that forward reaction until you are at equilibrium. All right, cool. So that's heat capacity, equilibrium constant, and reaction quotient. Let's get into the real bad boys here, which are enthalpy, entropy, and Gibbs free energy. So enthalpy is the first variable I want to talk about out of the three, and enthalpy is denoted by the character H. And so enthalpy is equal to internal energy plus, in parentheses, P, which is pressure, times V, which is volume. So H is equal to U plus PV. In other words, enthalpy is actually very similar to internal energy, only that it takes into account pressure and volume. So sometimes it's been called flow energy. So just know it's kind of a measure of energy. So what I've done is I've boiled down enthalpy into these three main things to know. The first is the difference between exothermic and endothermic reactions. So for exothermic reactions, the change in enthalpy is less than zero. So exothermic reactions have a negative change in enthalpy. In other words, they release energy or they feel hot. So if you were to put your hand on an exothermic reaction, you'd feel heat as this reaction releases heat, and you would also feel that it has a negative change in enthalpy. On the other hand, endothermic reactions absorb energy. If you were to put your hand on it, it would feel cold, and then you would also notice that it has an increase in enthalpy. So the big thing to take away here is that the change in enthalpy for an endothermic reaction is positive, and the change in enthalpy for a exothermic reaction is negative. The next place you might see enthalpy come up is in calculating the change in enthalpy for a reaction using the heats of formation method. All you got to do for this is say that the change in enthalpy for the reaction is equal to the sum of the heats of formations for the products minus the sum of the heats of formation for the reactants. And you'll be given all that information. All you got to do is add it up for the products, add it up for the reactants, subtract the reactants from the products. So that's all you got to do. One thing to keep in mind here is that elements in their elemental form have a heat of formation of 0. So sometimes in a problem, they might not give you every single heat of formation for all the products and reactants, and at which case, if you don't know that elements in their elemental form have a heat of formation of 0, you'll be freaking out. You'll be reading through the passage like, shit, I'm missing it. Where is this? Where is this? Like trying to pull out these heats of formation from somewhere else when in actuality they're 0. So for things like oxygen, its elemental form is O2, which is a gas. Hydrogen, its elemental form is H2, which is a gas. Zinc, it's a solid. So they're all different, but the big thing to know here is that if you're not given a heat of formation for a product or a reactant, then you're asked to calculate the change in enthalpy of the reaction using the heats of formation method. I wouldn't worry about it too much, just be like, okay, that must be an element in its elemental form. So practice this. I can describe it all I want, but really you got to go practice. Make sure you know how to do it. You probably will see this on the MCAT. Yes, heats of formation method. Go look it up. Do a few practice problems.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, the third thing you want to know about enthalpy is know the difference between the phase changes, basically. So you might be given something that's like enthalpy of vaporization or enthalpy of condensation, enthalpy of fusion, enthalpy of deposition, sublimation, all these different terms. So to be able to understand these enthalpy of phase changes, you need to understand, first of all, what each of these phase changes are. So vaporization, that's going from a liquid to a gas. Condensation is going from a gas down to a liquid. Fusion is going from a solid to a liquid, which is melting. Then you have freezing, which is the opposite of that. So that's going from a liquid to a solid. Then you have sublimation, which is going straight from a solid to a gas. And then you have deposition, which is going straight from a vapor into a solid. In terms of enthalpy change, I think it's important to recognize that two opposing phase change processes have the same enthalpy change. Only one has the negative of the other. So for instance, the heat of vaporization of water is 40.65 kilojoules per mole. Well, then going the opposite way, the heat of condensation of water is negative 40.65 kilojoules per mole. In the same way, the enthalpy change of fusion is equal to the negative enthalpy change of freezing, and then the enthalpy change of sublimation is equal to the negative enthalpy change of deposition. Another important thing to understand is that the heat of vaporization is much larger than the heat of fusion. In other words, you need a lot more energy in order to vaporize a liquid than to melt a solid. And why is that? Well, that's because when you are vaporizing a liquid, you are actually separating individual molecules. So in the instance of water, you're separating these water molecules for them to be able to become a vapor. When you're melting a solid, you're not separating individual molecules. Instead, you're just kind of making these molecules move a bit faster and then move around a little bit more until they become a liquid. All right, the last thing I want to talk about in terms of phase change is this really interesting phenomena that occurs in which phase changes occur at a single temperature. All right, so I think the best way to describe this is just to start with ice and talk about what happens as we add energy to this system. So let's say we start with a cup of ice and we want to melt this ice. So what do? So we start pumping in energy. And so what's going to happen is you're going to start with this ice. Let's say it's negative 20 degrees. You're going to heat till you hit 0 degrees. And during that heating phase, you're going to be inputting what is called sensible heat. So this is heat that goes into changing the temperature of the object, in which case this is ice. So once you hit that 0 degrees, what happens? Well, you get a phase change. So you start to melt that ice, and all this melting occurs at the same temperature. So you stay at 0 degrees and you keep inputting energy, but this energy doesn't go to changing the temperature. Instead, it goes into melting the ice. So you stay at this 0 degrees, you keep inputting energy in. This energy is called latent energy or latent heat. And latent heat is the type of heat that produces a phase change. So you're going and you're staying at 0 until you melt all the ice, and then at which point you start increasing the temperature of the now liquid. Again, you get this sensible heat input, and the temperature of the water keeps increasing till you hit 100 degrees Celsius, at which point it starts boiling, and it stays at 100 degrees Celsius as you keep inputting heat. So I'm putting in more and more and more, but it's not raising the temperature of the water. It's the water temperature is staying constant until you vaporize all that water, again through this latent heat that you're inputting. And then at that point, you just have this steam. And if you want, you can just keep inputting heat until you reach maybe infinite temperature. I don't really know what happens after that, but you can just keep increasing the temperature of this vapor as high as you want. You don't really get a phase change after that. So very important to know that these phase changes require a lot more input of energy. So if you want to go look up this plot, it looks like kind of like a stair stepper that just shows input of energy versus temperature. And the phase changes actually require more energy than increasing the temperature of the liquid or of the solid. So kind of interesting to me, I think, is that, when you're boiling a pot of water, that's all going to be at the exact same temperature. And you can't get boiling water at 200 degrees Celsius, right? I think that's kind of a misconception. You can't get like super hot boiled water. It's all the same temperature. All right, so that is enthalpy. Let's move on to Gibbs free energy, which is sort of tied in with enthalpy. The equation you're going to want to know for Gibbs free energy is that the change in Gibbs free energy is equal to the change in enthalpy minus temperature times the change in entropy. And what Gibbs free energy does is it tells us a little bit about spontaneity of a reaction. So I'm going to go through kind of like I did with enthalpy and talk about kind of some main aspects of Gibbs free energy to understand for the MCAT. So as I said, Gibbs free energy tells us whether a reaction is spontaneous or not. So what exactly do I mean by spontaneous? What is spontaneity? Well, a reaction that favors the formation of products at the conditions in which a reaction is occurring is considered spontaneous. So all a reaction has got to do in order to be considered spontaneous is it has to favor the products. And the sign of the change in Gibbs free energy tells us whether or not a reaction is spontaneous. So when a reaction is spontaneous, it will have a negative delta G, or a negative change in Gibbs free energy. On the other hand, if a reaction is non-spontaneous, it will have a positive delta G. So for an example, we have the reaction in which two magnesium atoms combine with an atom of oxygen gas to form magnesium oxide. That is a spontaneous reaction because it has a change in free energy of negative 1,137 kilojoules per mole. On the other hand, the dissociation of AgCl, which is Attorney General chloride, is not spontaneous. The delta G for that reaction is 55.6 kilojoules per mole. In other words, this reaction is barred from happening. And for non-spontaneous reactions, it's important to note that the reverse reaction is spontaneous, and then same for spontaneous reactions, the reverse is non-spontaneous. And this makes logical sense, right? If both the forward and reverse reaction were spontaneous at the same time, what would happen? It'd probably be some kind of reversible reaction. And I wonder if that's what happens in reversible reactions, like with enzymes. I don't know. Maybe some whack shit happens. I don't really know. But just know when you're given an equation, you're given a delta G. The delta G for the reverse reaction is just the negative of the given delta G. All right, the second place that you'll see Gibbs free energy come up is in determining the conditions in which a reaction is spontaneous. So this does have to do with spontaneity. I broke it down into its own little category because this is huge. You're definitely going to see a question like this. So first of all, going back to the Gibbs free energy equation, what factors play into spontaneity? Well, the equation is that delta G is equal to delta H minus T times delta S. So all three of those variables play a role. So the enthalpy change plays a role, and the entropy change plays a role, and the temperature also plays a role. So what the MCAT's going to do is it's going to ask something like this. Under what circumstances is the following reaction spontaneous? And then it will tell you a bit about the reaction. It'll say this is an exothermic reaction in which the entropy decreases. And then the answers will be, is this reaction always spontaneous? Spontaneous at low temperatures, spontaneous at high temperatures, or never spontaneous? And so what do we know about delta G and spontaneity? Well, when delta G is negative, that means it's a spontaneous reaction. So essentially, you need this equation to be negative. So you need delta H minus T times delta S to be negative, which means, if you do the math, that T delta S has to be greater than delta H. That's the only way this equation will be a negative number. So going back to the example that the MCAT gave us, we know that we have an exothermic reaction, so delta H is negative, and we know that the entropy decreases, so we know that that is also negative. So right now we have a negative minus a negative is equal to delta G. So in what cases is this delta G going to be negative? Well, if you recall, a negative minus a negative is the same as a negative plus a positive. So we need the negative of the enthalpy to outweigh the entropy. So in what cases is that true? Well, that is true when you have a really low temperature, right? Because when you multiply a very small number times the change in entropy, then that makes that term a little bit lower. And therefore, the negative enthalpy drives the overall spontaneity, and you can say that that's negative. So an exothermic reaction in which entropy decreases is only spontaneous at low T, which is actually the direct opposite of my dad, because for whatever reason, low T actually tends to make him non-spontaneous. Kind of weird. Anyways, using the same reasoning, you can determine the conditions in which a reaction is spontaneous for the 4 different conditions where you have exothermic or endothermic and then increasing or decreasing entropy. So what I'm going to do is I'm just going to present these 4 different conditions and tell you whether this is always spontaneous at low temperature, high temperature, or never spontaneous. And you can go through and you can kind of logic it out for each of these cases. And I kind of recommend you go do that just so you know how to use this Gibbs free energy equation. But just know for now what these 4 conditions are. You can put them on your note cards if you want. What I did is I just kind of logicked them out using that equation while I was taking the test. So the first case here is when a reaction is exothermic and entropy is increasing during the reaction. In this case, a reaction is always spontaneous. Next is the case in which you have an endothermic reaction and increasing entropy. And so these are spontaneous at high T or high temperature. The next case is an exothermic reaction in which entropy decreases, and these reactions are spontaneous at low temperature. Then lastly, we have the case in which you have an endothermic reaction in which you have a decreasing entropy, or the entropy decreases in the reaction. And these reactions are never spontaneous. And so what I like to do is I like to remember that endothermic reactions are unfavorable, and also decreasing entropy is unfavorable. So anytime you have the combination of both of those, then your reaction just doesn't do anything. It's not going to happen. No dice. It's a no-go. It's impossible. It's inconceivable. So again, I did not memorize these 4 trends. I just used the Gibbs equation on the test to kind of logic them out. You could memorize them. It's not that big of a deal. I just think the less you have to put in your brain to memorize, the better. And the MCAT is more about application anyways. So if you are used to applying these equations, then you might be able to apply them in different ways on the test as those come up. All right, so the next place that you may see Gibbs free energy come up is in terms of its relation to equilibrium. And so Gibbs free energy, as well as thermodynamics in general, are pretty tied to equilibrium. So there's an equation that ties together Gibbs free energy and the equilibrium constant, and that is that delta G is equal to negative RT natural log of K. And in this case, R is the gas constant, which you will be given, T is the temperature, and K is the equilibrium constant, which we just went over, which is the products raised to the power of their coefficients over the reactants raised to the power of their coefficients. And here, I think the most important thing to understand is what K will result in a spontaneous reaction, or what value of K will give us a spontaneous reaction. And so this is pretty intuitive. And I think a good way to kind of figure this out is to look at a plot of ln of x versus y. And so you'll see that in this plot, you cross over from a negative value to a positive at an x equal to 1. So that means when your K is below 1, ln of K will be negative, resulting in a positive delta G, which is non-spontaneous. However, when your K is greater than 1, you will have a positive ln of K value, which will mean your delta G is negative. So, in order to have a spontaneous reaction, your K must be greater than 1. That's all you got to know. Pretty easy. All right, the last thing that I want to talk about in terms of Gibbs free energy is stability, and in specific, protein stability. Protein stability is the main place that I've seen Gibbs free energy be associated with stability, but I think that these concepts can actually be extrapolated a bit further and be applied to a lot of different concepts. So this is important stuff. So let's talk about protein stability and folding and Gibbs energy, all in terms of a specific disease. So let's look at nephrogenic diabetes insipidus, which is a disease in which the kidney is not able to concentrate urine in response to the hormone vasopressin, which, if you remember from the renal physiology podcast, actually induces cells to increase the number of aquaporins in the membrane, which allows water to be reabsorbed. And so what happens in this nephrogenic diabetes insipidus disease is that these aquaporins are not able to fold correctly, so they lose their function. And typically only a single mutation is the culprit for this protein misfolding. And what happens then is all these misfolded proteins begin to aggregate and form these big insoluble clumps. So how do you apply thermodynamics, and more specifically Gibbs free energy, to protein misfolding? Well, let's say that we have our naive protein. It's not been folded yet. Let's say that a chaperone actually helps assist in folding of this protein. And so this protein can either fold into form 1 or it can fold into form 2. And now when you get this single mutation in the protein, you change the energetics of the folding. So let's say fold 1 has a delta G of folding of negative 1800 kilojoules per mole. And then fold 2, which let's say is the incorrect fold, has a delta G of folding of negative 2000 kilojoules per mole. This indicates that this second folding conformation is actually more stable than the first. And so over time, what's going to happen is that most of the folded proteins will start to become this second folded form, which is bad, and which forms these insoluble aggregates and leads to this NDI disease. So just keep in mind that if you're given a Gibbs free energy change for folding or for unfolding, know that the lower this delta G is, the more energetically favorable that reaction is. So again, this tells us nothing about kinetics, right? Let's go back to the example I just gave. Maybe this first folded form forms a lot faster, or the kinetics are a lot higher for that form. Well, then you're probably going to be forming a lot of that at first, but then let's say over a lot of time, you are going to form more and more of this thermodynamically favorable product, this misfolded protein. So just keep in mind that kinetics actually have a lot to do with this. So, maybe over a period of like 2 years, you have this second protein type just start to build up until you really start to get problems in your kidneys and you start peeing way too much water or whatever the symptoms are of this disease. All right, so that is a brief interlude into where you will see Gibbs free energy on the MCAT. Let's briefly summarize what I just talked about. So the Gibbs free energy will tell us whether or not a reaction is spontaneous. A negative delta G indicates spontaneity. And then you can determine the conditions in which a reaction will either be spontaneous or non-spontaneous by using the Gibbs free energy equation, which is delta G is equal to delta H minus T delta S. And then the third thing I talked about was how a K, or equilibrium constant greater than 1, will indicate a reaction that is spontaneous. And then lastly, I talked about how Gibbs free energy can tell us relative stability, right? The lower the Gibbs free energy change for reaction, the more stable that end product is, and that product will actually be favored thermodynamically. The last thermodynamic variable here is entropy, and this is going to be the shortest little bit because all I'm going to say here is that really you need to understand the second law of thermodynamics, which says that the entropy of the universe is always increasing. And beyond that, I wouldn't worry too much about understanding what entropy is. Focus your studying on enthalpy and Gibbs free energy. All right, before I go, I briefly want to mention the 3 different types of heat transfer, because you'll probably see these. The first is conduction, the second is convection, and the third is radiation. Conduction is the transfer of thermal energy between objects that are in contact with one another. And I have bolded and underlined the words in contact. So they got to be touching, they have to be in contact. And so I was working out the other day, I was in the gym, and true story, I was carrying a 45-pound plate, and I thought I had put it on the bar, and it wasn't quite all the way on there. It fell off and landed right on my foot, and I didn't break it or anything, but I did go home and I put some ice on it. So when I set the ice on my foot, that was conduction, right? I had a transfer of heat from my foot to the ice that was in contact with my foot. So that's conduction. The second type of heat transfer is called convection. And convection occurs when warmer areas of a gas or liquid, just some kind of fluid, rise to cooler areas in liquid and gas, again, which is a fluid. So in other words, This is heat transfer via fluid flow. So you can imagine, you just worked out, you're standing outside in the cold, and so there's this cold air near your warm skin. And so what happens is that your warm skin warms up some of that cold air, and warm air rises. So that warm air rises away and is replaced by cool air, which the same thing happens. That cool air is heated up, and you get this cycle of cold air coming in, getting warm, rising, and it's just like cooling through this fluid flow. The last type of heat transfer that I want to talk about is called radiation. And this is when thermal energy is transferred via electromagnetic energy. So the example here is, what you do in the summer on the weekends, and that is laying in front of the sun and letting all that thermal energy come down and hit your skin and hopefully make you tan or make you burn or make you get freckles, whatever happens. So just know that type of heat transfer is called radiation. All right, that does it for the Thermodynamics podcast. I hope this helped. As always, if you really liked this or, you thought it was funny or, helps you in your studying, please go give us a review on iTunes. Helps us with the ratings, helps us reach more people. I'm excited to announce that going forward in the next few weeks, I'm going to come out with an episode in which I interview Catherine, who runs the @thepremed account on Instagram, who is an MCAT tutor with Med School Coach. Really smart. We're going to talk a lot about MCAT study strategy. We'll talk about taking a gap year and also answer some Q&As from her Instagram page. So hopefully you tune in for that. Thanks as always for listening. See you next time.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.